chi-square tests. And chi-square tests are going to be really useful if you're looking at categorical variables. So up until now, I think you've mostly worked, if you did t-tests in your last lecture, things like that, you were working with quantitative values. And so here we're going to work with some categorical ones. So let me get in the live chat and let's get started. So yeah, we have a lot to cover today because we'll go over the analytical portion and then we have the coding portion of our lecture. So what we're going to be talking about today is continuing on with that hypothesis testing. So if that was something that was a little bit confusing to you in your last lecture, that's okay. We'll go over it a little bit again. So today's case is going to be looking at, like I said, chi-square tests. Our business problem for today is we're going to be looking at crime patterns that were reported by the Chicago Police Department in the United States. So our main question is, are the crime patterns that we have observed merely due to chance, or do they represent an actionable signal? So are we seeing any sort of relationship between crime and a particular place it's happening? So one thing that always gets discussed, and you guys are always really great at being really creative about alternatives for things you would need to be cautious of when you're doing any of these statistical tests or any of the things we've talked about in the past. And just like that, there are always caveats with your data. Here is the same thing. If you found a relationship between crime patterns and location, it's always important to think about, could there be other factors involved in that? Socioeconomic status, is that location a poorer area, a wealthier area, what goes on there, things to think about outside of just what your data tells you. And we'll talk a little about that as well. So our hypothesis, or we're going to explore this hypothesis about these two categorical variables to see if they're independent of each other or if there's a relationship. And so the way that we're going to do that is we're going to work with a contingency table. So the first thing that we need to do is look at our data set. Before you can make your contingency table, we need to look at our overall data set. And here you can see that we have our ID. So each one of these is a crime that occurred. And then it tells you the type of crime. We're interested in this primary type: burglary, battery, theft, what type of crime actually occurred, and then the location. So we have a lot of data here, but our hypothesis, let's remember, is we want to explore whether or not there are particular crimes that happen in particular locations. So, this is our overall data set. We have quite a few columns. We know about the location, but we care most about this location description, if it's in an apartment, a hotel, something like that, and the type of crime. So one thing to point out, and I kind of mentioned at the beginning, is, you might be asking, how is this different from in the past when we've learned about correlations? Can't you just look at a correlation and figure out if crime is related to the location? But actually, these are, like I said before, categorical variables. So because you have things like a hotel or motel and a theft, those aren't numbers. You can't, those aren't quantitative numbers that you can, put into a correlation matrix and come up with that correlation. So here, what we're going to do is make a contingency table so that we can perform a test on two categorical variables. So the contingency table is similar to a frequency table. It's basically saying, how many times did this thing occur? So a frequency table normally tells you how many things of a particular category occurred. Like, how many times did this person go running? How many times did this person go walking? It's one category. But with a contingency table, you can have two or more categories. So when we make this contingency table, it's still a frequency table in a sense, but now we can say, how many times did two things occur? So if we look at a contingency table for our data, what this is basically saying is of all of the crimes that occurred in our data set, 10 were arson and 10 also occurred in that abandoned building. So there were 10 crimes that were arson in an abandoned building. So that's what we're basically saying here is when you see these numbers, it's the count data for how many times did this crime happen in this location. So we are still making a frequency table, but this way we can incorporate more than one category. You can, here we're only going to look at two for the sake of simplicity. There are contingency tables that have more than two categories. So this is our contingency table, the way it looks. You can see we have a lot of zeros. We also have a lot of categories, right? We have quite a few different locations and quite a few different types of crime that have occurred. So we have a lot of things that are zeros. We have some sporadic data throughout. So one thing that we can do is we could actually compress some of this data. So we could make wider categories. So maybe what we can do is, since we have a lot of these zeros, we could group some categories together. Like maybe we could make all of the violent crimes, we could kind of compress them down and call them, call it a category violent crime, and put everything, any of those crimes in with that particular category. So the benefit of doing something like that is that we avoid losing data. So, we don't want to just cut out here like stalking. So we can kind of see that most of these are zeros, but you don't necessarily want to cut out your data. You have heard in the past how important it is to be really careful about cutting out any data, and to make sure that you have a legitimate reason for doing that. So, even if there's only, in this case, there's probably, I think, zeros, maybe, we have 2 stalking. So we don't necessarily want to cut that out, even though there's only 2, but we could maybe put it in with another category, a different type of crime, so that we can preserve all that data, but have a more legible table that can also give us some hints about patterns that we could see. So does that make sense so far about, kind of contingency tables? And what the contingency table means? Let me know in the chat if I'm going too fast or if anyone's confused at the beginning, because it's important to understand what that contingency table is, and so we can keep moving. So for exercise 1, like I said, we kind of can go ahead and group some of those categories. We can kind of compress it down. So that's what we've done here. And like I said, we'll have a coding portion next, so we'll go over how all of this was done. But what we did for primary type, for the type of crime, we turned all of those different categories into, I think, 7 different categories. So we have theft, property damage, violence, and related. So we took all of these different categories and we compressed them down into 7. And the same with location. We went ahead and classified those into hospitals and related, colleges and related, so that we can still see all of our data and observe those patterns, but it's just a little bit more legible, and we can push some of that sparse data into a larger category. So here is the contingency table for those grouped categories. So as you can see now, we have fewer offenses categories, we have fewer locations. So let's look at this contingency table. And why don't you put in the live chat, what conclusions? Do you see any patterns from this table? And again, I can kind of clarify that what we're looking at here is, for example, this 252 is how many crimes occurred in an airport or related area, and they were dangerous practices. So there were 252 that were dangerous practices and occurred in an airport. Here we have 60 that were other offenses occurred in an airport. So that's what these are counts. These are the counts of how many crimes occurred in those locations. So do you see any patterns that stick out about this data? Okay. Yeah, so really good observation so far. So someone pointed out that there are no more zeros. So that's much more legible, right? We got rid of a lot of those zeros, that sparse data. That's a really good point that now everything has numbers in it. We can still see trends. We have not gotten rid of our trends, but we've just made this so now we don't have all of that kind of those blank spaces. And someone else pointed out, or a couple of people pointed out, that we have a lot of theft related crimes. So if you're looking down here, it seems like we have a lot of theft related crimes, especially in this residential and stores and related. It seems like theft is a really big one. So yeah, those were great observations. One of the possible answers here is that they occurred in residential areas, stores, and street areas, which we talked about. You can see it's what we're looking at here to look at those trends. It's just where are the largest numbers compared to smaller numbers. It's just looking at the counts. That's the only trend we're looking at so far. So you can come up with a couple of different things for where you have those highest numbers. Okay, so since we have, so far, this is the raw count data. But what we need to do when we're working with contingency tables is we need to actually make these a percentage instead of raw counts. So if you can see percentages, that also helps you to visualize your data a little bit better. So before, when we just had counts, in this case, it is pretty clear to see, okay, yeah, we have large numbers here. But if we can get a percentage, that's more informative for us. So we need, and I will explain in just a second why that is. But we need to calculate percentages, and then we need to choose how we're going to normalize our data. So when we make this contingency table, you can either normalize your data based off of the columns or the rows. And so when I say that you normalize it, that would mean that if you go ahead and you normalize your data, in this case, we have normalized it by row. So if you added up all of these, it would equal 100%. So that's how we've normalized our data here. And the reason why we do this is because it's a little bit more informative. So now when we look at our table, we can see that 57% of sexual offenses occurred in a residential and related area. So that helps us to see of the total of all of the sexual offenses that occurred, where are they occurring the most? Well, they're occurring the most in residential and related. So when you think about how you're going to normalize your data, you think about what you want to know, and you can do it both ways, and you should do it both ways, because you can see different trends if you normalize by row or by column. So if we normalized it by column, the only difference would be that here our column would equal 100% at the bottom. And then, we will look at that as well and go over what that means. But for the sake of looking at this table, this is percentages now, and we've normalized it by row. So again, that means that all of these add up to 100%. And that helps us just to see now, it helps us to see, where are the majority of certain types of crimes occurring, right? So we can see here in a lot of cases that most crimes are occurring in a residential and related. So we see that, violent crimes, most of them are occurring in residences. We can see that 55% of other offenses are also occurring in residential areas. So that percentage helps us to interpret where are the majority of things happening. Another way you can see these patterns really easily is to make a heat map. So if you had a really big table, kind of like this one, it can be hard to pick out those trends. You're looking at a lot of numbers, and it can be hard to pick out those patterns. Here, it's pretty obvious, right? We can see the higher numbers are kind of in this residential, but that may not always be the case. So looking at it as a heat map is a good visualization to say immediately we can see where are there any patterns? And we can see it based off of color. So when we're interpreting this heat map, you've probably seen in previous lectures, the darker color in this case is a higher percentage. So we're looking at the percentage of offenses in each type in that location. So what we've done is it's the same table, just as a heat map now. So, it's that same percentage data, but now it's a little bit easier to see what we were seeing before because it's in color. So when we look at that, at this heat map, what conclusions can we make from this plot and table? And I kind of gave that away a little bit in talking about the meaning of this, but go ahead and put in the live chat kind of, what you're seeing with these, with this plot and with the table. And if you're having trouble with, I think there's a comment, if you're having trouble seeing the colors, I'm not sure if that's like a technical or if it's like, if you're dealing with color blindness, I know that can also be an issue. I would say that go ahead and look at this. This is the exact same table. So if you're having trouble seeing the color for whatever reason, go ahead and, you can look at these numbers. These will be the same. So, yeah, so go ahead and put in either based off of the numerical plot here, which is percentage, or based off of the heat map. It should be the same thing. Okay, so yeah, everyone's putting in the chat. Awesome. So you can see some pretty clear trends because you see these two very dark lines. So that is another reason, that, well, one of the reasons that we do this normalization is so that you can pick out those trends. But like I said, so we kind of talked about this where it's pretty clear about the residential and related have a lot of crimes, street crimes happen a lot. So another thing we should do is, like I said, instead of normalizing by row, we should also normalize by column. So in this case, what we would be doing is we're kind of flipping it. So whereas before every row, let me actually go back up to our percentage. Where here, the row equaled 100%, so that we could say of all the sexual offenses, 0.15% occurred at the airport. But if we were to do this by column, which is our next heat map, we would be saying of all the airport and related crimes, we take all of the crimes that occurred in an airport. How many of them are sexual offenses? How many of them are violent crimes? How many of them are property damage? So instead of saying here one more time that of all the sexual offenses of, all of the counts that we had for sexual offenses, how many occurred at each location? Here we're saying of all of the offenses that occurred at a particular location, how many were of each of these types? So that can be a little bit complicated to think about, when you're flipping your normalizations, but you should do both. Because here, so this is, we can kind of see a different pattern now that we normalize it by column instead of by row. So again, let's go ahead and look at this and what conclusions can you make from this heat map? Do you notice anything, the difference, I guess, between this heat map and maybe the one up above? So that you can see, and again, darker colors will indicate a higher percent of offenses in that location. So we can also kind of, I'll explain this column here. So for example, of all of the crimes that happened in stores and related, we can see the darkest region is theft. So most of the crimes that happen in a store are theft related. So, and let me know if you have any questions about that normalization between rows and columns. Okay. So you can create the heat map just based off of the count data as well. You don't have to normalize it. You could still look at it and just see where are the higher numbers. But typically, if you do this normalization, it's easier to see those trends because you are looking at a percentage. Now, when you have 50% versus 40%, that's a little bit more obvious of a trend than if you had 500 versus 400 for your count data. Okay, so again, good observations. We can see that we still have a lot of the theft related crime and violence and related crime. So one thing that we want to look at here is when we're also trying to decide, is there a pattern here? Is there a relationship, right? Because this whole lesson is about hypothesis testing. So the whole reason that we're making this heat map and this percentage table is because we want to know, is there a relationship between these two variables? So I guess I'll ask you all, do you think that there is a relationship based off of this heat map, based off of this one where we, this heat map and the previous where we normalized our data based off of column or row? Do you think that there's a relationship between location and crime? Okay, a lot of yeses. I know I'm not giving you a whole lot of time to answer, and that's just because I want to make sure we get all of this in. So do let me know if you're having any sort of confusion or anything like that in the live chat, and I'll try to slow down or explain something else again. So the initial answers were yes, and that is correct. There is a relationship. So the reason that we know this is because if there was not a relationship between location and crime, then we wouldn't see any sort of pattern. We would kind of see an equal distribution of the shading. We would not see, theft, crime maybe happening more in stores than in a bank or related. We wouldn't see, this distinct pattern of dark shading if they were independent of one another. So there does seem to be a kind of relationship. So, and that's kind of explained here, that we can see that the color hues vary across different crime locations, so they still support the existence of interactions. I will say, and we'll talk about this as we talk about chi-square test, one of the downsides to a chi-square test is that you have to use count data. So you have to have those raw numbers, and you cannot tell the strength of the relationship. So what we will determine here is whether or not there is a relationship between crime and location, but we can't necessarily get specific about, is one location more strongly related to a particular type of crime or not. All we know is that there is that relationship. So those are a couple of things to keep in mind if you want to apply a chi-square test to your data. So let's talk a little bit about, like I said, whether or not there is that relationship, whether or not crime and location are independent of one another. So in the last lecture, I think you talked a little bit about a null and alternative hypothesis. I will kind of emphasize that again. So a null hypothesis is basically no relationship. Whenever you are writing or creating or thinking of a null hypothesis, think of no relationship. So our null hypothesis is that primary type has no relationship to location description. It's independent. So our null hypothesis, no relationship between the two. Our alternative hypothesis would be that there is a relationship between primary type or the type of crime and the location description. So if they were independent of one another, then the probability of one happening would be the same as the probability of another happening. So let's talk about this section here. So when we're thinking about independent variables, that means that you can have one variable that has no relationship with another. So that means that as one variable, if one variable stays the same, it doesn't affect that other variable. So that second variable can increase or decrease, and it has no effect on the other. So does that kind of, so let's say, for example, let me see, I'm trying to think of a good example for independent variables here. So let's say that let's say that the amount of food that I eat has no effect on weight gain. So that would mean that I can eat no food for a week and that will not affect my weight. I can eat a lot of food, a ton of food, eating a lot of food, and that will not have any effect on my weight. Those would be independent variables because it doesn't matter what I do. It has no effect on weight. But if there is a relationship, then maybe if I eat more, my weight goes up, and those are related. So that's kind of maybe not a great example of independent variables, but independent variables mean that it doesn't matter what one does because it doesn't affect the other one. So that's a way that we would a way that we would calculate that is that if there is no relationship between two things, then the probability of them happening, the probability of these two independent events is the probability of the first one times the probability of the second one. So they have an equal probability of occurring. So the reason that we're talking about probability here, and the reason that we're talking about this is because to do our chi-square test, we have already calculated our actual data. We have come up with the percentages of crimes that have occurred in a particular location and the type of crime. But what we need to do is calculate another contingency table that says, what if they were independent of each other? What would the probability be, or what would the count or the percentages be, or I guess the count data be if there was no relationship? So the reason that we're doing that is because we want to know if these two variables, if they are not related, we need to know what would that data look like, and is it different from what we actually got, from what our real data looks like. So that's what we're going to do here, is we're going to calculate a contingency table that is hypothetical data for what if these two things were not related? What would the counts be if they were not related? And the way we calculate this is by taking the probability of the first event times the probability of the second event. So as an example, this is basically our null hypothesis table. So the way that we're going to do this is we would say, for example, we know that of all the offenses, we know that 40% of them were thefts. Of all of our offenses, we know that 40% of them, 40.2% were thefts. And that of all of the offenses, 36.56 happened in residential spaces. So if these two things are not related, then the way we would calculate that is to say the probability that a theft happened and it was in a residential space is 0.402 times 0.365. So that would be 0.14 or 14%. So if location and crime were not related, then 14% of our thefts should have been in residential spaces. If they were not related, 14% of our thefts should have been in residential spaces. So I'll repeat this one more time because I think this part is a little bit confusing and is important to know. So what we're doing is we're calculating this table that is a hypothetical table to say what would the counts be if there was no relationship between location and type of crime. And so the way we calculate each one of these boxes is to say, in this case, of all of the, like, let's say the way that we get this number is that we want to take the percent of all the crimes that occurred that were dangerous practices, of all of them, just all the crimes that were dangerous practices, what percent? And we would want to say, multiply that times how, of all the crimes that happened, how many were airport and related. And if we multiply those two, then hypothetically, we should have 112 crimes that occurred that were dangerous practices and in an airport. So for this part, the way we did this one is that hypothetically, if there was no relationship and we wanted to get the counts for how many crimes that were thefts happened in a residential space, we would say how many of all of the offenses, how many were thefts, 40%, and how many of all the crimes how many happened in a residential space? 36%. So how many crimes happened that were thefts and in a residential space? That should be 14% of crimes. So that would be, when we know that percentage, we know we have 267,000 cases in our data set. So that would be 39,000 cases. So we can see that here. Here's that count for residential and related and theft crimes. So we have thefts that occurred in a residence, basically. If there's no relationship, we should have 39,000 of them that happened. So let's actually go and check that. So let's remember, if there's no relationship, we should have seen about 39,000 crimes that happened, thefts in a house, in a residential area. So if we go back up to our counts, which is here. So we have residential and related, and we were looking at theft. So here we have only 28,000, right? So if there was no relationship, we would have seen, oh, now I'm for 39,000, I think. And here we're seeing 28,000. So our test, our statistical test is that significantly different from our null? Is that significantly different? Can we say that that is significant, that there is some kind of relationship? So let me just pause really quick for a second and see if there are any, let me check the chat and see if there are any questions about this. So yeah, the purpose of calculating this hypothetical table is to say, is that hypothetical table significantly different from our actual table? So we needed to calculate this because we needed something to compare, right? We needed to figure out that statistical significance for this chi-square test. We need something to compare it to. So we always compare our null hypothesis to our alternative hypothesis. And our alternative hypothesis was made using our original contingency table with the actual counts. So we need a null, and our null is this contingency table here, which has the ideal table. If they were independent, these are the counts that we would see if there was no relationship, because the probability of one happening is the same as the probability of the other. Okay. Okay. So this was our ideal table if they were independent. And then, yeah, we kind of talked about this section here. The idea is that we want to see how the difference, how much our actual table deviates from our null hypothesis table or our independent variable table. Okay, so we are given the answer here. If we were to conduct a chi-square test on our contingency table, we will find that the p-value is extremely small, essentially 0. We can thus reject the null hypothesis and conclude that primary type and location description are not independent. So what that means is that we did our chi-square test on this table and our actual count table and found that they were significantly different. We had a p-value that's very, very small, which means that when you have that small p-value, it is unlikely that that happened by chance, that what you're observing was just due to randomness, right? That's the whole reason that we do a statistical test, is because we're curious to know if whether the trend we're seeing is just due to randomness, if it's just something that could have happened, that just could have happened randomly. And so when we get that really low p-value, really close to 0, that means that there was a very little or a small probability that your observed results happened by chance. It means that it's most likely that there is an actual trend there or an actual relationship. It is statistically significant. Okay, so exercise 4. Our client is interested in violent crimes around residential areas. In order to gather some information, you talk to a police officer who tells you the following. From my experience, violent crime offenses do not discriminate by location around residential areas. I have seen everything happen everywhere. If you wanted to use a chi-square test, what would be the null and alternative hypothesis? And what would a p-value of 0 mean? So let's first talk about that first part. Go ahead and say, what do you think the null and alternative hypotheses would be if we wanted to test this? This officer has made a statement that from his experience, violent crime offenses do not discriminate by location around residential areas. I've seen everything happen everywhere. So what would be the null and alternative hypothesis if we wanted to test this? And we will go over how the p-value will be calculated. Yeah. So they gave us the answer for the p-value. So I see a lot of questions about calculating that, and we will go over that in the coding section. So for now, it's just kind of giving away the answer that the p-value was very close to 0. And I guess while you're putting your answers in, I will clarify that when you have this p-value that's essentially 0 or very small, you will never have a p-value of 0. So whenever you get an output that says, 0.00, that doesn't actually mean a straight 0. It means it's probably very, very close to 0. But you'll never actually have a p-value of 0. So that's kind of the second part of this question, which we'll get to in a second. But I wanted to clarify that you never actually get that p-value of 0. You may get a p-value of 1 times 10 to the negative 30 or something like that, implying it's very, very, very small, but you'll never get that p-value of 0, because that would imply that it's impossible for your relationship to have occurred. And so you're never going to have 0 because there's always a chance it was due to randomness. There's always, the chance can be very, very small that it was due to randomness, but it's never 0. Okay, so yeah, let's go ahead and talk about our null and alternative hypothesis, and then what a p-value of 0 or a p-value very close to 0 would mean. So here, our null hypothesis, like I said before, think of null hypothesis as no relationship. So our null hypothesis would be that that primary type or that crime and the location are independent. They're not related. And we would be looking at the violence and related group and the locations that belong to residential and related. So what we would be saying is that the violence and related group in crime and residential and related have no relationship. And our alternative is that there is a relationship, that the variables are not independent. So kind of what we talked about before, but in this case, our hypothesis is specific to those violent and related crimes in residential and related locations. So so let's go ahead and talk about this part. So what do you think if we got a p-value of 0? And we'll talk about the contingency table in a second. So if we had a p-value of 0, or close to 0, what would that mean? And yeah, so your p-value is up to you. There is some debate about what the best p-value is. It's typically a p-value has been, or a significant p-value is anything less than 0.05. But I think especially in science, that is shifting towards 0.01 or 0.001. So it's something you definitely should set at the beginning of your hypothesis test. You should not change it after you get your results to make your results significant. But there is debate about whether or not. A p-value of 0.05 determines significance, or whether it should be smaller, like 0.01. And yeah, so if we had a p-value close to 0, we could reject the null and say that it's likely that there is a relationship between the violent and related crimes in residences. So this was our contingency table where we looked at violent crimes. And remember, we had grouped those together originally into a wider category called violent and related crimes. But in this case, since we're testing those specifically, we would want to pull all that data out and make it more granular, put it back into its original categories. So those were 4: assault, battery, homicide, and kidnapping. And then we have the locations where, again, we would break that back out and have all of the locations from our original data set, the count data here. So we'll kind of give you the answer to this one, that a chi-square test was used. So the way we would do that chi-square test, again, is that we would need to calculate another contingency table with the calculations for if these were independent of one another, what would the counts be? And then compare it to this table and see if it's significantly different. So we went ahead and did that behind the scenes, and we'll do that in the coding portion, but found that there is a significant difference. So you can almost see that here as well. Looking at this count data, you can kind of see that assault and battery, there are, clusters where assault and battery seem to be happening, first of all, more often than homicide and kidnapping. There are more counts for that assault and battery as you go down, but also that there are when you're looking at the locations, you can see it kind of clusters. It seems to happen more often in apartments. It seems to happen more often in residences than it does in any of these other locations where crimes have occurred, like a hotel. It seems like residences, you're getting more of that assault and battery than you are homicide and kidnapping. So it does seem to be like there's a relationship when you're just looking at it with your eyes. But then when we go ahead and make that our contingency table with the ideal counts, if they were independent of one another, those were also statistically different. So we can confirm that we got that chi-square test. It had a p-value close to 0. Remember, we're never going to have a p-value of an absolute 0. So that would be how we would test that hypothesis. So the next thing that we can look at is, we talked about at the beginning how one of the downsides to a chi-square test is that it has to be categorical variables. And so one of the ways that we could take a variable and we could make it a categorical variable. So let's say we wanted to look at time. So, one way that we can do this is you could, if you had time, you could group it by day of the week, because day of the week is a categorical variable. Monday, Tuesday, Wednesday, Thursday, Friday are not, representative of anything. They are kind of arbitrary names that we give to a day of the week. They don't represent anything necessarily numerical. So we can kind of categorize different things so that we could do a chi-square test and look at those different types of patterns. So if we wanted to look at time, in this case, we can do day of the week. If we have that data, we could take our time data, which normally you wouldn't necessarily be able to do a chi-square test with just time. But here we can, because we're going to group it into day of the week and make it a category. So we could do this chi-square test by, we're making our heat map here of if we wanted to see if there are any trends for the type of crime and the day of the week. So instead of location, if we were interested in type of crime and day of the week, we could make that heat map again for the percentages. And then we can see some of those patterns based off of, or see if there are any patterns, or if there is a relationship based off of the shading of our heat map. So let me see if this is listed. It doesn't really, okay, so our hypothesis here that we're going to test is there a relationship between day of the week and primary type? So again, our null hypothesis would be that there's no relationship between the type of crime and the day of the week. Our alternative hypothesis is that there is a relationship. So for exercise 5, looking at this heat map, do you think that we would reject the null hypothesis or accept it? So basically, do you think that there is, based off of this heat map, do you think that there's a relationship between the day of the week and the type of crime? And we should also, I should clarify that we normalize, so since this is percentages, it's normalized by day of the week. So let me explain what that means really quick. So again, when we have our day of the week here, so let's say for this first day, this is all of the crimes, all of this will sum to 100%. Each column will sum to 100%. So what that means is for all of the crime that occurred on this first day, how many were non-criminal, how many were other offense, how many were prostitution. So this is just dividing up for each day of the week of, you know, what types of crimes were occurring in the greatest percentage. So we normalized this here by day of the week. So meaning that all of these sum to 100% of all the crime that happened on that first day. So let's go ahead and answer this. Do you think that based off of this, is there a relationship between day of the week and type of crime? Yeah, I think 0 is Monday, if I remember correctly. And yeah, so it is we have summed this by or sorry, normalized it. I think there are a couple of questions. We normalized it by day of the week. So this whole column will sum to 100. If we normalized it by row, then the row would sum to 100. But in this case, we normalized it by day of the week. So if you added up all of these percentages for day 0 or Monday, that would sum to 100. So we're looking at, you know, what percent of the crimes that happened on Monday were prostitution? What percent of the crimes that happened on Monday were narcotics, were non-criminal? Okay. So again, I think good observations in the live chat, and I think you're kind of getting the hang of this, that in the heat map, if you see these differences, we don't see a normal distribution on the days. We really are seeing differences that pop out on particular days. I think an obvious one is here for this non-criminal, which isn't very specific, but of these non-criminal crimes, a lot of them are happening on Monday and on Thursday. Yeah, the heat map looks different from, you know, if we just had that normal distribution where everything was independent. So we can see that the proportion of offenses don't seem to be consistent across all of the days. So yeah, we see these differences in the shading, and that's a good indication that there might be a relationship. That's a key way to look at it. So we will go ahead and perform our chi-square test behind the scenes, and we get a p-value very close to 0. So that supports the contention that primary type and day of the week are not independent. And I think, okay, so we can discuss this for just a minute longer. So, you know, we notice this by our shading. And so what we would have done then is we would have calculated our null hypothesis table, saying if these things were independent, and the way we would have done that, I'll reiterate one more time, is that we would have, like, to calculate this box, we would have said I'm talking about if we had calculated our null hypothesis table, the way we would do that is by taking the percent of weapons violations that happened of all the crimes. How many were weapons violations? So let's say that was 10%. And of all the crimes that happened, how many crimes occurred on Monday? let's say that that's 15%, or 0.15. So then we would have multiplied, 0.1 times 0.15, and then that's how we would have known the percent of crimes. If it were independent, the percent of crimes that would have been weapons violations and would have happened on a Monday. So if they're independent of each other, you take the percent of, the chance of that one crime happening times the chance of it being a Monday, multiply those, and that would be the chance that a weapons violation occurred on a Monday. And that would imply if there were no relationship between those things, they have an equal probability. What's the chance of one happening times what's the chance of the other happening? Okay. And yeah, so there's a good comment that it feels a little bit like cheating because we already know the p-value, and that is true. So this, it is very hard to tell looking at this if there is what type of relationship there is, or if there is a relationship. You can get some indications because we can see, a little bit of different shading, but we don't see anything super obvious, like with our previous table where we had some dark lines that were occurring for particular places and particular crimes. And so that is why it's important to do that statistical test against our null hypothesis table to say, is this statistically significant? And you can also tell a little bit of that strength of a little bit of the strength of the relationship by that p-value. So if we had a really, really low p-value, then that says that let's say our p-value here is only 0.04. Well, that's pretty close to 0.05. It's still statistically significant if we called it 0.05, but that is, saying that compared to a table where maybe we got a p-value of 0.00001, that if we got that 0.04, then there's a little more likelihood that could have happened by randomness, that it maybe isn't statistically significant, especially if you had established your p-value cutoff at 0.01, then that 0.04 isn't significant at all. So it can be hard to tell just by looking at it, is there a relationship here? But your p-value and that statistical significance can be a good indicator of whether or not you have that significance. So, okay. And there's a question about whether this was normalized by row due to the value percentage. Well, it shouldn't be. This should be normalized by column. And I think it is, because if it were normalized by, here you have something around 50 and 50, and then you have maybe something here that's between 0 and 10. It's a little bit hard to tell, to be 100% sure, but if this table is correct, which I would suppose it is, then these should all sum to 100. The rows should not. But since I don't have actual numbers here, I can't double check that for you. Okay. Are there any other questions? Otherwise, we can take a break a little bit early and then start on our coding portion a little bit early. So let me just check really quick for other questions. And if anyone has, we have the time. So if anyone has any questions about confusion on, these contingency tables or anything like that, feel free to put them in the chat. Okay. So let's go ahead. It is 7:55 for you all. So let's take a 10-minute break, and we'll come back at 8. I'm trying to do the time conversion. So 7:55, that would be 8:05 for you all, 9:05 for me. So let's come back at 8:05. We'll do a 10-minute break and we'll start on the coding portion.